Hello, everyone. Welcome to AWM Pitt Grad Student Seminar. Happy Pi Day. Today we have two speakers from the University of Oregon. The first one is Tatyana Benko. She is a PhD student. Her talk is double boxes and double dammers. Please go ahead, Tatyana.
Okay, thanks. Happy to be here. Today I'm going to talk about my research with my advisor called double boxes and double dimers. Okay, so I'm going to start with our main result, and then we'll probably just get to like some definitions and things of everything. Oh no, I'm gonna get rid of this. Well, okay, um, so I want to fix A, B, and C as some natural numbers. And our main result is this equality of generating functions. So on the left-hand side here, I have a generating function, which is going to enumerate something called a double box configuration. And we're going to get to that. And then on the right-hand side, I have the generating function for plane partitions squared times the generating function for boxed A by B by C plane partitions. There we go. Okay, so this equality of generating functions is given in a geometry paper by Gullimpur and Poole. And what we're going to do is give a combinatorial proof of it. Okay, so we're going to start with some definitions of things leading up to the definition of the double box configurations. So first of all, a plane partition is a two-dimensional array of non-negative integers, weakly decreasing in the rows and the columns. So here's an example. And we can think about it as a stack of boxes in a room, just rotate it a little bit. So this is the back corner of the room. So this first row here is right here. So 4, 4, 3, 2, 1. Okay, my next definition I want to talk about is called a dimer configuration, also called a perfect matching, and I will probably go back and forth between the two. So a dimer configuration of a graph is a subset of the edges such that every vertex in the vertex set of the graph has degree 1. So here's a couple of examples. So on the hexagon graph, in blue is my perfect matching. So I've chosen these edges and they cover all of the vertices of the hexagon graph exactly once. Here's another example for the grid graph. The pink edges are my dimer configuration. So again, they cover all the vertices exactly once. Okay, so there's a bijection between plane partitions and dimer configurations on the hexagon graph. And it's sometimes referred to as the focal or bijection, and it kind of goes like this. So we think about our plane partition as a stack of boxes in the corner of the room. So here's a little example. We've got 2 boxes here, one here, one here, and one here. And then I'm going to draw a line corresponding to each of the different tiles that I have here, corresponding to the box faces and the walls. And then if I just kind of like connect up all of the endpoints here, there's a hexagon graph in the background. And so then I'm going to just get rid of the outline for all of the boxes. And what I'm left with is a dimer configuration on the hexagon graph, where the edges I've chosen come from these orange ones here. All right, so now let's get to what is a double box configuration.
Just a quick question.
Yeah,
Why is it called a folklore bijection?
that's a good question. So I don't know. I learned this from my advisor. I don't actually know if other people call it this or not. This is what he calls it. So that's a good question. And I think also because it's like a visual thing happening here. Okay. So now to the double box configurations. We're going to build this thing out of plane partitions. So I want to take 3 plane partitions, A to 1, A to 2, and A to 3. And I want to think of them as stacks of boxes and place them in R3 in a certain way. So I want to put eta 1 at 0 BC. And when I say base it, I mean put the very back corner of the room at that point. So eta 1 lives here. Eta 2 is at A0C, so it lives over here. And eta 3 is at AB0, so it lives down here. And all three of these plane partitions might intersect starting here at the point ABC. So we call this the intersection space. And in the intersection space, if there's boxes there, this is also a plane partition, and we'll call it eta int. And we want this to be the pairwise intersection of all the plane partitions. And then we have this condition, which basically it just says that every box that is in this intersection space, we want it to come from at least two of the plane partitions. So it comes from either two or three of the plane partitions, not just one. So we'll see some examples of that. But first, so we define kind of like different types of boxes depending on how many of the plane partitions they came from. So if we have a box in our configuration here, which, we call a box a type 3 box if it comes from all three of the plane partitions. So type 3 box can only live in the intersection space. It's called a type 2 box if it comes from two of the plane partitions. And again, those can only live in the intersection space. And then a type 1 box if it's only in one of the plane partitions. And by our condition that we have, these type 1 boxes can only live outside of the intersection space. So eta int has type 2 and type 3 boxes. Okay, great. So here's a couple of examples. So in all of these, we have A, B, and C being 1. So in this first example, I have one box in my intersection space right here. And it is a type 2 box. It comes from eta 2, this one, and eta 1. Okay, over here, I have a similar looking configuration, but my box in the intersection space right here is a type 3 box now because it comes from eta 2, eta 1, and eta 3. Okay, here's a non-example. So this is not a double box configuration because we have one box in the intersection space here, but it only came from eta 1. So that's not a double box configuration. And lastly, it's okay if eta int is empty. That's fine. All right, so there's one more thing that we need to define these double box configurations. So we have these triples of plane partitions that we place in R3 at these base points, and we want them to overlap in eta int as type 2 or type 3 boxes only. Okay, great. But we say that like two triples of plane partitions give us the same double box configuration if they have the same multi-set of boxes. And here's an example to say what I mean by that. What I mean is they have the same type 1, type 2, and type 3 boxes. And so what can change is which two plane partitions a type 2 box came from. So here's an example. Over here, here's my intersection space. I have one box, and it comes from eta 1 and eta 3, those boxes overlapping. Over here, I have a different triple of plane partitions. Here's what it gives me. And again, in the intersection space, I have a type 2 box. This one came from eta 2 tilde and eta 3 tilde. So on the left, this guy came from eta 1 and eta 3. And on the right, this guy came from eta 2 tilde and eta 3 tilde. And because both of these configurations have the same multi-set of boxes, they both have a type 1 box here, 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 and a type 2 box in the middle. I consider this to be the same double box configuration. Okay, and these kinds of type 2 boxes that we're considering here, where I can kind of move them around and put them in different plane partitions. We call these a movable type 2 box. And so there are then like two different kinds of type 2 boxes, movable and unmovable. So we just saw an example of a movable. Here's something that would be unmovable. My double box configuration. Again, I have a type 2 box in my intersection space here. It came from Eta 2 and Eta 1. It is unmovable because I can't make the same double box configuration this box into Eta 3 because there's no boxes below it, so it wouldn't be supported. So this is an example of an unmovable type 2 box. And then here's another example with a movable type 2. So this one's a little bigger. So in my intersection space here, I have two boxes right here. So here's those two boxes. So this first one is a type 3 box. It came from Eta 2, oh, right, this one. And Eta 1, it was this one. And Eta 3 was this box. And then I also have a movable type 2 box. So this came from Eta 2 here. And one, two, oh no, it's not an Eta 2, sorry. It's an Eta 1 and Eta 3. But I could move that and put it into Eta 2 instead. I could take it out of Eta 3 and put it in Eta 2, for example. Okay. So now we have that definition of the double box configuration. So let's introduce this generating function, which we saw in the beginning in our equality of generating functions. So given a double box configuration, I want to let's let chi of eta be 2 to the number of connected components of movable type 2 boxes in that configuration. And then the size of eta is going to be the sum of the size of all the plane partitions, which is just the number of boxes in each one, minus the size of the intersection space, so the number of boxes there. And so what this ends up counting is we count the number of type 1 boxes plus the number of type 2 boxes plus 2 times the number of type 3 boxes. And so this is what our generating function looks like. We're going to sum over all the double box configurations, weight by this chi of eta, and then times q to the size of eta. So in this example, let's just see. Chi of eta is 2 to the number of connected components of movable type 2 boxes. So in this is the same as the previous example. So I just have the one movable type 2 box. So this is 2 to the 1, so I get 2. And then for the size of eta, let's see, eta 1 has 4 boxes. Eta 2 has 5 boxes in it. 1, 2, 3, 4. And Eta 3 has 8 boxes. I might have moved them around a little bit. And then Eta int has 2 boxes. So I get a size of 15. And so the contribution of this double box configuration to the generating function is 2 times q to the 15. All right, so that's kind of my first object, my double boxes. So next I want to introduce my second object, which is the double dimers. So a double dimer configuration on a graph G, and given some node set, so this is just some subset of my vertices that I've defined, some special set. So the double dimer configuration is a subset of graph edges such that vertices in V minus n have degree 2 and vertices in n have degree 1. So here's an example. So I have this hexagon graph here, and my node set that I'm defining are these nodes on the outside face of my hexagon graph. I've defined those. I've said these are my nodes. And so then I take a dimer configuration on the normal graph, and I take a dimer configuration on the graph minus those nodes. So I have not matched any of these guys. And then I put those two on top of each other. And what I get is a configuration that has doubled edges, could possibly have loops. I don't have it in this example. And I get paths between all of the nodes because for all my nodes, they're only connected by a blue edge, not an orange edge. So they all have degree 1. And so they're all going to be connected. Here's another example where I have some loops showing up. Okay, so kind of the idea of what we do is we take these double box configurations and we're going to map them to a double dimer configuration with a certain set of nodes and a certain pairing of those nodes. So here's the particular pairing that we're gonna use. So I want to fix my A, B, and C. And on my hexagon graph, I want to define these nodes. So on this L1 line here, I want to take the A, like little a nodes closest to corner A. And on L2 here, I want to take C nodes closest to corner A, and I'm going to color them red. And similarly, I'm going to make these guys all blue and these guys green. So these are all my nodes and they have different colors. And I want to consider the tripartite node pairing of these nodes, which means that all of the nodes get paired up with a node of a different color. So there's only one way that can happen. It's like this triple rainbow thing. Because any other way you connect up nodes to a different color, you're going to get paths crossing, which we can't have. So this is the node set and the node pairing I want to consider. Okay, so then what I'm thinking about here is these objects, double dimer configurations with the node set I just defined and the node pairing I just defined. So here's the generating function for those objects. I want to count them. And then kind of the idea, what we do is we map the double box configurations to these tripartite double dimer configurations, kind of via the same folklore bijection that we talked about with just the plane partitions to dimer configurations. So maybe let's see. You can kind of see, so the base points of the plane partitions, eta 1, eta 2, and eta 3 are going to get projected here. And here's where eta int is going to live. Okay, let's just look at some examples. So here's one of my double box configurations. So I take each of my 3 plane partitions. So this one's eta 2, this is eta 3, and this is eta 1. And I apply this folklore bijection to get a dimer configuration for each one. And then I overlay all 3 of these such that this red point is aligned in each one. And I get this thing. I get a triple dimer configuration. And notice I have these paths here, just kind of how we said in this rainbow, triple rainbow pattern. And because I chose A, B, and C to all be 1, I have one of these paths in each of my sections. Okay, here's just a few more examples of these. So here's an example where I had the type 3 box in the middle. So then that means this box overlaps with this box, overlaps with this box. And so when I put all those together, I have these triple edges in the middle here. Okay. Here's an example with a movable type 2 box. And when I put all those together, I get a loop in the middle. Okay. So this is kind of how, this is the visualization of how we map the double box configurations to the double dimer configurations. But you might be thinking like, this is a triple dimer configuration, and I had said double dimer configuration earlier. So the mapping is easy to see, but then to show, we actually show that these generating functions are equal to each other. And that involves showing that, you can remove a certain single dimer configuration from these triple ones to actually get to the double dimer configurations that we were talking about. So the mapping is pretty easy to see. In showing the generating functions are equal, there's a little more to do. And I'll maybe show you just like one example of why it's not just a bijection between these things. So here's an example of, so these are two different double box configurations split up into their single plane partitions. And when you put like all three of these together, they give you the same tripartite double dimer configuration. So it's not a bijection between the two, I guess is what it is to say here. And what it comes down to is like where the movable type 2 boxes are, because these correspond to the loops in the double dimer configuration. Okay, so I will end here kind of just with an idea of the proof of an overview here. So we want to prove this identity of the generating functions. And the way we do that is we first show that instead of looking at double box configurations, we can look at these tripartite double dimer configurations. And the whole point of doing that is that then we can apply what's called a condensation relation to both sides of this equality here. And all that means is we show that both sides satisfy the same recurrence relation. And so it kind of looks like this. So the right-hand side, we use graphical condensation. And then on the left-hand side, we use something called double dimer configuration. Okay, so that's kind of the overview that we use to prove this result using combinatorial methods. And yeah, thank you for listening.